Resource Center's Summer Climate Academy. I am both Associate Director of Rutgers Climate Institute, and along with my colleague Jean Herb of the Rutgers Blaustein School of Planning and Public Policy, I co-direct the newly established Climate Change Resource Center. Other than today's presenter, Professor Anthony Broccoli, and our Rutgers team, you are all muted, so to communicate with us, please type your questions into the chat box. To find the chat box, hover your mouse at the bottom of your screen, and a series of circles will be displayed. There's one circle that looks like a dialog bubble. If you click that, the chat comes up and you can type your questions there. You are welcome to type your questions into the chat box throughout today's presentation. We suggest that you type to all participants because that's where we will be monitoring the questions as they come in. And after the formal presentation, we will address as many of your questions as time allows. Before we dive into the presentation, I'd like to give you a bit of information about the newly formed New Jersey Climate Change Resource Center. The center, which is housed at Rutgers University, was created by legislation signed by Governor Murphy this past January to create and support the use of impartial and actionable science to advance government, public, private, and non-governmental sector efforts to adapt to and mitigate a changing climate. The center is intended to conduct applied research, create planning tools, develop technical guidance, undertake pilot projects, and provide practical support for addressing climate change in New Jersey. The center also has as part of its mission to connect actionable research to policymakers, planners, practitioners, the media, communities, students, and other individuals through outreach, training, and education. In keeping with that mission, we're very pleased to present today's inaugural webinar of the New Jersey Climate Change Resource Center, and the first in the Summer Climate Academy. Our speaker today is the atmospheric scientist Anthony Broccoli. Dr. Broccoli is a distinguished professor at Rutgers University, chair of the Department of Environmental Sciences, co-director of Rutgers Climate Institute, and director of the Rutgers Center for Environmental Prediction. Among his other scholarly accomplishments, Dr. Broccoli has been the chief editor of the Journal of Climate, and he is a fellow of the American Meteorological Society and fellow of the American Association for the Advancement of Science. He's also the co-author of the recent book, Beyond Global Warming: How Numerical Models Revealed the Secrets of Climate Change. Before I turn it over to Dr. Broccoli, a quick reminder to put your questions in the chat, and we'll get to as many as possible during the Q&A session. With that, it's my pleasure to turn it over to Dr. Broccoli to speak on the state of the climate in New Jersey.
Marjorie, just one quick thing. A few people mentioned in the chat they're actually not able to send to all participants, so anyone send your questions to all panelists instead. Thanks.
Thank you, Matt.
Thanks very much, Marjorie. It's a pleasure to have all of you tuning into this webinar this morning. And I'm going to give you a little bit of a preview of a report that is currently under development on the state of the climate, focusing on New Jersey. And in preparing that report, I have some very able collaborators. Brian Fry, a recent graduate of our meteorology program at Rutgers, Dave Robinson, the New Jersey state climatologist, and the person who just introduced me, Marjorie Kaplan from the Rutgers Climate Institute and the New Jersey Climate Change Resource Center. So their help has been essential to producing some of the science that I'm going to share with you this morning. Now, for the overall approach that I'm going to take in today's talk, I'm going to begin by focusing in on climate change globally, and then we'll take our telescope and zoom on in and look at climate change as it's being felt here in New Jersey and as it will be felt in the future. So we'll start out with a global view, and then we'll proceed to a more local view. We'll start out by discussing the primary driver of climate change, and that's the increase in greenhouse gas concentrations in the atmosphere. These measurements have been going on since the late 1950s, Dr. Charles Keeling of the Scripps Institution of Oceanography set up an observatory to measure atmospheric carbon dioxide at Mauna Loa on the Big Island of Hawaii. Those measurements have since been taken over by the NOAA Earth System Research Lab, and they have measurements at many places around the world, like Mauna Loa, at pristine sites, so that the measurements are not affected by local industrial or tailpipe emissions. And what these measurements show universally is a dramatic increase in the amount of carbon dioxide in the atmosphere. When the measurements began in the late 1950s, the concentrations were about 315 parts per million, and they're now about 415 parts per million. So in a fraction of a typical human lifetime, the amount of carbon dioxide in the atmosphere has increased by about 30%. Now, you may have been hearing a little bit about how the COVID-19 pandemic has reduced greenhouse gas emissions, and that is the case. But keep in mind that greenhouse gases accumulate in the atmosphere. They have a long residence time. So the concentrations will still be going up despite whatever reduction in emissions takes place during the pandemic, but perhaps the rate of increase will slow for 2020 as compared to 2019. Now we can take a longer view on greenhouse gas concentrations in the atmosphere. For this, we have to look at measurements that have been made in tiny air bubbles in the glacial ice of Greenland and particularly Antarctica. And those measurements show that prior to the Industrial Revolution, the concentrations of greenhouse gases in the atmosphere were somewhere in the range of maybe 275 to 285 parts per million. And they began rising around the turn of the 19th century as the Industrial Revolution really started to gain force. And the increases have become more rapid ever since that time. In this diagram, the red line at the end shows the Mauna Loa curve, and I've extended this old figure to bring it up to date to the 415 parts per million where we are today. Now, there are older ice bubble records that go well beyond the period shown here, and they indicate that the current CO2 levels are the highest at any time during the past 800,000 years. And there's other evidence that suggests that they're the highest perhaps in the last 3 or 4 million years. So we're seeing an unusually high concentration of greenhouse gases in the atmosphere, primarily carbon dioxide. Going along with that increase in carbon dioxide in the atmosphere, we have seen an increase in global temperature. These are data compiled by the NASA Goddard Institute for Space Studies. The scale is in degrees Fahrenheit, and the temperatures as shown as temperature anomalies. That's the difference in temperature between any particular year and a baseline period. For this data set, the baseline period was arbitrarily chosen to be the period from 1951 through 1980. So that defines the 0 point on this graph. There are large variations, relatively large variations in temperature from year to year, and I'll talk a little bit more about those in a few minutes. To try to smooth out some of those year-to-year variations, the red curve is the result of a statistical smoothing technique that tries to smooth out variations of shorter than 5 years. The overall impression you get when you look at this curve is a rise in temperature in the early 20th century, period from about 1940 through 1970 or 1975, where the temperature didn't change very much, just some fluctuations up and down, and then a more rapid rise in temperature from the 1970s up through the present. And that rise in temperature is now roughly 2 degrees Fahrenheit compared to where temperatures were at around the turn of the 20th century. And looking at global temperature trends, we find that the past 6 years have been the 6th warmest years on record. 19 of the 20 warmest years have happened since 2000. The average rate of warming over the period since 1880 is about 0.16 degrees Fahrenheit per decade. But when we focus in on the more recent period since 1980, the average rate of increase has been just under a half degree Fahrenheit per decade. And as a recent note, January of this year was the warmest January on record, just barely. You see the data for the last several years, going back to 2015, from the NASA Goddard Institute for Space Studies record. The black curve is where we are so far in 2020. The green curve is 2016, which to date is the warmest year on record. So we were a little bit warmer than 2016 in January and in April, not quite as warm in February and March. And we'll see what happens over the course of the rest of this year to see whether or not 2020 can contend with 2016 for the warmest year on record. But seeing this graph raises the question of why temperatures vary as much as they do from year to year. And so I'd like to say a little bit about the factors that can influence year-to-year temperature variations. So we have a fairly busy figure here, but really not too complicated. At the top, the green curve shows global temperatures going back to 1950. So we're zooming in on the last 70 years or so of this period of time. The two curves in the middle box represent temperatures separated by land versus ocean. So the blue curve is based on sea surface temperatures. The orange curve is based on land surface temperatures. So a couple of things are evident there. First of all, land surface temperatures vary more than temperatures of the ocean, and that stands to reason. Ocean water has a large heat capacity, so it's slower to respond to changes. And then down at the bottom, we have the sea surface temperature from a region in the tropical Pacific that is strongly influenced by the El Nino phenomenon. So where the curve is above the zero line, those are indicative of El Nino events, at least when the curve goes far above that zero line. And when the curve dips below the zero line, we're looking at La Nina events, or events where the waters of the tropical Pacific Ocean are unusually cold. So now let's talk about some of the influences on year-to-year temperature variations. You may notice three little symbols at the bottom of the global temperature chart. Those indicate the timing of large volcanic eruptions that ejected a lot of sulfur dioxide gas into the stratosphere. The first one in 1963 is Mount Agung in Indonesia. The second one in 1982 is El Chichon in Mexico. And then in 1991, Mount Pinatubo in the Philippines. And global temperature decreases, and the decrease can last for several years following these large volcanic eruptions that eject sulfur dioxide into the stratosphere. Sulfur dioxide, once it gets into the stratosphere, combines with water vapor there to form droplets of sulfuric acid that reflect some sunlight back to space. And as a result, the Earth cools a bit following these eruptions. Now, the volcanic eruptions are not the only thing that can affect year-to-year temperature variations. As you might have guessed from my mention of El Nino and La Nina, these phenomena have an effect on global temperature as well. In fact, when we get large El Nino events, temperatures spike upward during and just after those El Nino events. Generally, the peak warming happens about 3 to 6 months after the peak of the El Nino event. So we see with these red lines to help you identify the temperature increases, look at the top graph again, and you'll see that along and following each of those red lines, we see an upward spike in global temperature. Similarly, the La Nina events, when the waters of the eastern tropical Pacific Ocean get unusually cold, are followed by downward spikes in global temperature, which again, you can see some of them stronger than others. And you may also be noticing that often strong El Nino events are followed by strong La Nina events, but not always. The last big El Nino in 2016 wasn't followed by a strong La Nina event, but that last big El Nino in 2016 is what pushed the temperature that year to what is currently the warmest on record. Now, what about the future? Well, we can't say exactly when volcanic eruptions will happen in the future or when El Nino events will happen in the future, at least not more than a few months in advance for our ability to predict El Nino. So what we try to do is run our climate models many, many times, averaging them together so that we smooth out the effects of these ups and downs from year to year in global temperature, and then project what the temperature would do based on different scenarios of greenhouse gas emissions into the atmosphere. And so what are shown here are the results from two different scenarios. The blue curve is a scenario in which greenhouse gas emissions are rapidly decreased, so the amount of carbon dioxide stabilizes in the atmosphere after another decade or two, somewhere in the 400s. And then the scenario shown by the red line and the orange band, which is indicative of some of the variability around that scenario, represents a scenario in which greenhouse gases increase and approach 1,000 parts per million by the end of this century. So under the low emission scenario, we get just about another 1 degree Fahrenheit of warming between now and the end of the 21st century. Whereas under the higher emission scenario, the amount of warming globally is more like 5 or 6 degrees Fahrenheit. Now, we don't know exactly which one of these scenarios will play out. So these scenarios are not intended to be specific forecasts of the future, but to give us instead an idea of the range of possibilities that can happen. A warming Earth also means less sea ice, particularly in the Arctic. Sea ice in the Arctic reaches its annual minimum during sometime in the middle of the month of September. And the amount of sea ice has been decreasing quite substantially since good satellite measurements began in the late 1970s. So this graph shows that for the period from the late 1970s through the 80s, the area of sea ice, the extent of sea ice in the Arctic in September, averaged around 7 million square kilometers. But there has been since a rapid drop, and so that recent years have been averaging more like 4.5 million square kilometers, with 2012 being the record lowest year with only about 3.5 million square kilometers of sea ice extent in the Arctic. The reduction in Arctic sea ice extent is important because ice is much more reflective than ocean waters. And when the ice disappears, that means there's more absorption of sunlight, which is a feedback that can help to warm the climate system even further. And as you may be aware, the warming in the Arctic has been larger and has been happening more rapidly than it's been happening for the globe as a whole. This reduction in sea ice has made it possible for cruise ships to travel the Northwest Passage. This is the route that the first cruise ship to make this passage took in 2016. And as recently as the 19th century, explorers, Franklin expedition, were getting stuck in the ice and starving and dying trying to travel the Northwest Passage. And now it's navigable by a luxury cruise ship. So these changes are very substantial changes that have been taking place in the Arctic, and they've happened in a relatively short period. Also in the high latitudes, not just the Arctic, but also the Antarctic, we've seen increased melt or increased calving or both of the Greenland and Antarctic ice sheets. For Greenland, the average mass loss in the 1980s was about 50 gigatons per year. For the period from 2010 to 2018, it increased to about 280 gigatons per year. And what's shown in the right are satellite measurements of the area of Greenland that was undergoing surface melt during July of 2016, I believe this is, 2012. It's that year when we had the very reduced Arctic ice. And in the right-hand panel, at that time, there was melting going on virtually everywhere on the surface of the Greenland ice sheet. One of the only times that had happened since the satellite measurements began. There's also been increased mass loss from Antarctica, increasing from about 40 gigatons per year from 1979 through 1990 to about 250 gigatons per year from 2009 through 2017. And as this ice melts, it contributes to sea level rise. Now let's focus in a little bit closer to home on what's been happening here in New Jersey. These are New Jersey temperatures going back to 1895, compiled by NOAA from National Centers for Environmental Information. And you see that for a small area like New Jersey, there's even more year-to-year variability in temperature. The temperature can go up and down by several degrees Fahrenheit from year to year because weather patterns are variable. And when you're talking about a relatively small area, it makes a big difference whether the wind is blowing from the north, bringing in cooler air, or from the south, bringing in warmer air. So we do see large year-to-year variations. But again, attempting to smooth out those variations with the red curve here, we see something that's broadly similar to the trend in global temperature. We see a gradual warming in the early part of the 20th century, a period from, say, 1940 through 1970, where the temperatures fluctuated up and down, but there wasn't really much of a long-term trend. And then a more definitive upward trend since about 1970. And the warming since the record began in 1895 is about 4 degrees Fahrenheit. So putting that into some context, New Jersey has warmed about twice as fast as the global average. The global average was about 2 degrees, New Jersey about 4 degrees. As with the global average, the warming has been more rapid since 1970. Of the 20 warmest years on record in New Jersey, 14 of them have occurred since 2000. And the warming trend has been largest in winter, where it's warmed about 6 degrees Fahrenheit, and smallest in spring and fall, where the warming has been only about 3.5 degrees Fahrenheit. Projections from NOAA, based on the National Climate Assessment for the late 21st century, indicate that New Jersey temperatures could range anywhere from 8 to 14 degrees Fahrenheit above their pre-industrial values for a high emission scenario, and anywhere from 5 to 8 degrees Fahrenheit above pre-industrial for a low emission scenario, keeping in mind that we're now about roughly 4 degrees warmer than during pre-industrial times. So anywhere from a doubling to a tripling of that warming under a high emission scenario, and then maybe a little bit more warming under a low emission scenario. One of the potential consequences of warming, particularly in summer, is a prevalence of harmful algal blooms. And the reason for this is that warmer waters are more favorable for the growth of certain types of toxic algae. And of course, in New Jersey, we saw some prominent HAB, harmful algal bloom events in 2019, including closures of some of the beaches on our lakes in northern New Jersey because of these harmful algal blooms. And in fact, a recent study based on satellite data has found evidence that the frequency of these HABs has been increasing in lakes throughout the world. So this isn't just a New Jersey issue. Moving on to sea level. Here are sea level records for New Jersey. Again, quite a bit of variability from month to month and year to year, but a strong upward trend. At Atlantic City, sea level has risen just under 18 inches since 1911. You'll hear a lot more about sea levels in New Jersey in the webinar that my colleague Bob Kopp will be giving on Wednesday at noon. So I'm just going to go through a few features here. First of all, the rate of sea level rise on the New Jersey coast has been more than twice the global average. And that's primarily due to the subsidence of land in New Jersey at the same time the water levels are going up. The rate of sea level rise is also affected by changes in ocean currents and gravitational effects brought about by the melting of the Greenland and Antarctic ice sheets. And projections from a Rutgers-led study that was done late last year indicate that the likely range of further increases in sea level for 2030, about half a foot to just over 1 foot relative to the year 2000. And by the likely range, we mean there's a 2/3 chance, 2 out of 3 chance that sea level rise will be in that range, and a 1 out of 6 chance that it would be either below, or a 1 out of 6 chance that it would be above that range. For 2050, the likely range is from right around 1 foot to just a little over 2 feet. By 2100, the amount of sea level rise depends more strongly on the emissions scenario. Under a low emission scenario, anywhere from 1.7 to 3.9 feet is the likely range. For a high emission scenario, the range is 2.3 to 6.3 feet. How about precipitation in New Jersey? Precipitation is a highly variable quantity. It's variable from year to year, and there are also periods of several years, such as the drought of the 1960s, the very profound drought conditions that occurred in the 1960s, where precipitation can remain above or below normal for several years. But looking at New Jersey precipitation trends overall, there has been an increase, about a 7% increase between the period from the first 3 decades of the 20th century to the last 3 decades, 1990 through 2019, about 7% more precipitation during that latter period. As I mentioned, Precipitation exhibits large interannual and decadal variability, with some indication of larger variability since the 1990s. The two wettest years on record have occurred during the past decade, for instance. And projections indicate an increase in annual precipitation of about 10% by the late 21st century, with larger increases in winter and spring, and little or no change in summer and fall. But keep in mind that these precipitation increases will be occurring in the context of increased evaporative demand due to higher temperatures. So just because precipitation is going up, that doesn't necessarily mean there will be more water available, because evaporation will be increasing also. I'd like to conclude my talk today by discussing extreme events, because these are often the events that are most impactful in terms of weather and climate here in New Jersey and elsewhere. This table is showing the different years of the 21st century so far across the top. Those are the columns starting in 2000. And then the different rows are the different calendar months, January at the top, December at the bottom. And what I'm about to do, and this is based on a graphic that has been prepared for many years by Dave Robinson and Jeff Huffman of the New Jersey Department of Environmental Protection. I'm going to color in one of these boxes red if that month was one of the top 5 warmest months for that time of year, or in blue if it was one of the top 5 coldest months. So when we do that, we see 38 unusually warm months, top 5 warm months, and no unusually cold months during this century. So our temperature extremes have been dominated by warm extremes. In fact, looking at this chart, it's becoming clear that there have been even more warm extremes in the last decade than there were in the decade prior. So this is a significant impact associated with climate change. This graphic shows the number of heat-related hospitalizations and emergency department visits during the warm season, May through September, from 2014 to 2013. And there's an upward trend in both hospitalizations and emergency department visits, indicating the impacts of some of these extreme events. And in fact, when we look at the relatively high levels in 2010 especially, and also a high level of emergency department visits in 2011, there was some very warm weather with triple-digit heat during those summers. Extreme warm events can also contribute to air quality issues. Higher ozone levels typically occur during heat waves. And an analysis of data shows that when ozone levels are high, there are more asthma cases that come to emergency departments, particularly among children. Now, I'm going to talk about extreme precipitation next. But before I do that, I want to explain what we mean when we talk about a 100-year event, whether it's a 100-year storm or a 100-year flood. We hear these terms a lot, but we often don't get a clear explanation of what they mean. A 100-year event, which typically refers to a flooding event or an extreme weather event, is an event that has a 1% or a 1 over 100 probability of occurring each year at a particular location. So similarly, a 50-year event would have a 1 over 50 probability or a 2% probability of occurring each year. The number of years, when we talk about a 100-year or 50-year event, is known as the return period or the recurrence interval. But that doesn't mean that these are going to happen like clockwork. It's a common misconception that if we just had a 100-year event, that it won't happen again for another 100 years or so. Although that could be the case, the probability remains at 1% every year, no matter what happened in preceding years. Now, there's another caveat that's very important here. These statistics are determined from past climate data and assume that the climate is stationary. That is, that there aren't any systematic trends. But we know there are systematic trends in temperature that we've talked about, and maybe some trends in precipitation. Are there trends in the frequency of these extreme events? Well, that's the question that was asked as part of the National Climate Assessment using data from throughout the United States. What they did was use data from the first half of the 20th century to determine how much precipitation had to fall in a 2-day period at each location around the country to qualify to be the 5-year rain event, the 5-year 2-day rain event. So in other words, how much rain would have to fall to have a recurrence interval of 5 years? And then using those definitions, they went through the rainfall data to see how often these events actually occurred. Now, because there are variations from year to year, and here they used 5-year periods to try to average things out a bit. During the first half of the 20th century, there were some 5-year periods where these extreme rainfall events were a little bit more frequent, and other 5-year periods where they were a little bit less frequent. But there was no systematic trend. But since 1970, we have been seeing a very definite upward trend in these extreme precipitation events, so much so that we're now seeing them happening 40 to 50% more often than they did in the early part of the 20th century. Now, to give you an example of one of these events, here's a graphic from Dave Robinson's office, the New Jersey State Climatologist office, showing a map of rainfall in New Jersey during one of these extreme events that happened in parts of Gloucester, Camden, and Burlington counties on the 19th and 20th of June in 2019. The precipitation at several stations was over 5 inches for this less than 24-hour period, including just over 8 inches at Tabernacle in Burlington County, 5.76 at Medford Lakes, and just under 5.5 inches at West Deptford. That 24-hour total of 8 inches at Tabernacle, if we use past data, has an average recurrence interval of about 70 years. So it's a very unusual event. But such events are expected to become more frequent in the future. One of the impacts that these heavy rainfall events can have are on wastewater infrastructure, specifically combined sewer outflows. In many cases, particularly in our older cities, the same sewers carry sewage and runoff from the streets, stormwater. And under normal circumstances, the sewage goes to a wastewater treatment plant and isn't discharged into a river or other waterway. That's the slide on the upper left. But when heavy rains occur, the volume of water in that combined system can become so large that both stormwater and sewage get discharged into waterways, raising bacterial levels in those waterways. Now, at the bottom, those two panels are showing that sea level rise can also affect these combined outflow systems by making it harder for water to be discharged into the waterways, whether it's stormwater or otherwise, and actually backing it up into the system. And sea level rise has tremendous impacts on coastal flooding, as you can obviously see in this image from Hurricane Sandy. Sandy produced a lot of effects on health as well. Some of those effects come from the contaminants that are spread by the floodwaters. Some of those effects can come from mold that occurs in homes that were flooded by the coastal flooding from storms like Sandy. And there can also be psychological distress and emotional issues for people, especially children, who live through these traumatic events. But it doesn't take a storm as significant as Sandy to produce serious coastal flooding. This is Tropical Storm Melissa. Many of you may not even remember the Tropical Storm Melissa happened in October of last year. It formed from an old cold front that had passed off the coast and started to acquire some tropical characteristics. At first, it was classified as a subtropical storm, but then eventually it became a tropical storm. It did a couple of loop-de-loops far off the mid-Atlantic coast before it eventually moved out to sea. But because it sat there for a long period of time with onshore winds pushing waters towards the New Jersey coast, tide cycle after tide cycle, the waters in our back bays along the New Jersey shore, this graph is from Barnegat Bay in Ocean County, went well above normal. So here we see tide elevations 2 to 3 feet higher than normal. And that produced very significant flooding. Here's some of that flooding on what's a mostly sunny day. Those are people kayaking on what's normally a road along the bayfront of Barnegat Bay, with instead 2 or 3 feet of water pushed onshore by this relatively innocuous storm. In fact, it doesn't even take a storm to produce flooding. Unusual astronomical tides are enough to produce flooding. These tides may be produced one day a year of flooding at Atlantic City in the 1950s. But for the period from 2007 to 2016, there were 8 such days. And based on projections of future sea level rise, by 2030, we might see more than 2 weeks of days with tidal flooding, not necessarily consecutively, of course. By 2060, 85 days. And by 2100, about 2/3 of the days will be experiencing tidal flooding. So sea level rise is important because it's raising the baseline for flooding, whether that's flooding from major storms like Sandy, flooding from much more minor events like Tropical Storm Melissa or a typical winter nor'easter, or even the kind of sunny day flooding that can occur. All right, I'm going to sum up now. New Jersey's been warming at about twice the global average rate. Precipitation has also been increasing, about 7% more in recent decades than it was early in the 20th century. And sea level along the New Jersey coast has risen almost 1.5 feet since 1911. What about the future? The amount of future warming will depend upon future greenhouse gas emissions. This is why it's so important that if we want to prevent the worst effects of climate change from happening, we need to reduce greenhouse gas emissions, and the sooner the better. We expect more warm extremes and fewer cold extremes. Heavy rains will become more intense with some of the impacts, flooding impacts associated with those heavy rains. And rising sea level will lead to increased frequency and intensity of coastal flooding. So that's it for this morning. I thank you for your interest in this topic and for participating in this webinar, and I'll be happy to take some of the questions that you've been sending in and during the course of the presentation. Thank you.
Thank you, Tony. If we were all in person, you'd hear a lot of clapping, I'm sure. We now have some time to get to the questions. Folks have been typing in the chat box. I'm going to turn over to my colleague, Dr. Carrie Ferraro, who's been diligently monitoring the chat and who will direct your questions to Dr. Broccoli.
Okay. Thanks, Marjorie. So I will ask the questions as they were received in order. So Tony, the first question was from Jean Fox. She asked if, in addition to the Big Island, I think she's referring to when you were talking about Mauna Loa, if there are any other Scripps pristine places in the United States.
Let's see. I think the other monitoring station in the United States is at Point Barrow in Alaska. But the other ones are mostly spread throughout the world. There's a desire to get good geographic coverage, particularly covering a range of latitudes, because most of the emissions of carbon dioxide happen where people live, and there are more people in the northern hemisphere than there are in the southern hemisphere. So monitoring carbon dioxide measurements at locations at a number of different latitudes help us understand how carbon dioxide circulates through the atmosphere.
Great, thank you. Our next question was from Steve Carson. He asked a question regarding the graph that you had shown on global temperature anomalies and the separation into land versus ocean. He wanted to know, are sea surface temperatures of the water or of the air above? He's assuming that what is called land surface temperature is the air temperature above the land.
And that is right. Thanks for that question, Steve. Yes, land surface temperatures are the temperatures taken at weather stations, and they're commonly measured in a very uniform way that's specified by international standards, 6 feet above the surface. The measurements of ocean conditions are sea surface temperatures. There are also more limited measurements of what are called nighttime marine air temperatures, being exactly what they sound like. Temperatures measured from ships at nighttime so they don't have to worry about the effects of the sun. And comparisons have shown that there isn't a big difference between the trends that you would get. In fact, there's very little difference between the trends you would get from sea surface temperatures and nighttime marine air temperatures. But the sea surface temperatures are much more numerous and give us better coverage.
Thank you. Our next question is from Mike Alcott, who asked, how likely, in your view, is it that the rapid warming of the Arctic is weakening the jet stream, and in that manner causing stuck weather patterns in temperate latitudes?
That's a very good question, Mike. This is a hypothesis that has been put forth by a number of people, including my colleague Jennifer Francis. And I would say the state of that hypothesis right now is that the jury is still out. There has been evidence both pro and con in the published literature. I think some of the strongest evidence for stuck weather patterns may be coming from summer, and the role of the Arctic in that is maybe not quite as clear, but there are certainly other very large impacts that the changes in the Arctic have, particularly locally and maybe on a larger scale, but we're still trying to understand the effects on atmospheric circulation.
Our next question is from William Matalewicz. Sorry if I butchered your name there. He asked, where are we in Milankovitch cycling, and how would this impact the current accelerated climate change?
So for those of you who may not be familiar with the term, Milankovitch was a Serbian astronomer who postulated in the 1940s that the sequence of ice ages and relatively warmer periods in between were a result of small changes in the shape of the Earth's orbit and the tilt of the Earth's axis. Right now, we are in an interglacial period. And the best evidence we have is that we would probably have a wait of another maybe 20,000 years or so before we would enter the next opportunity for an ice age from Milankovitch cycles. However, with increased greenhouse gases into the atmosphere, there have been studies done to suggest that with this much carbon dioxide in the atmosphere, it might not be possible to go into an ice age, even if we had the orbital configuration that we will have 20,000 years from now.
Thanks, Tony. Our next question is from Matthew Rivas, who asked if there have been any studies to measure the increased photosynthesis from HABs, from harmful algal blooms.
That's outside of my area of expertise, so I don't know the answer to that question. So I think I'm going to have to punt on that one.
Good. Anthony Purcell asked if the 7% increase in precipitation is statistically significant, or is it outside of the natural variability?
Yeah, I think it would be unlikely that it's statistically significant. Trying to determine whether it's outside the range of natural variability is really hard because precipitation is so variable, not only from year to year, but also from decade to decade. Certainly, 125 years of records is a relatively long period of time, but it's not a long period of time when you're trying to see fluctuations that may persist for several decades. So I think given that models are projecting an increase in New Jersey precipitation as the climate warms, and the climate has been warming in New Jersey, there is some reason to think that we're seeing a physically important signal there, but I think it's far from clear that all of that 7% increase can be connected to warming. I think we would have to see more evidence to say that.
Great, thanks, Tony. Suzanne Chiavari asked, will the sea level rise that causes the 200 plus days of flooding in AC by 2100 impact saltwater intrusion to the coastal plain aquifers?
Yes, absolutely. Not only can it affect the aquifers, but it can also affect things like the intake that the city of Philadelphia has for its drinking water on the Delaware River. The salt front is normally well below that intake, but in some drought years, like during the 1960s, that salt front has gotten uncomfortably close to those intakes. But with higher sea level, you're essentially pushing that salt water further up the estuaries. So yes, that is a significant concern.
Kara, I think we have time for maybe one more question.
Okay, thanks. So then our last question is from John Callahan, who asked what your thoughts are on the projections of tropical storm tracks as well as activity. Even if more severe storms occur, are they projected to impact the New Jersey Mid-Atlantic region?
That is a great question. So there's a couple of things embedded in that question. First of all, we have model projections that suggest that in the future, tropical cyclones, or hurricanes as we call them in the Atlantic, will have the potential to become more intense as a result of the warming of the ocean waters. That's where hurricanes derive their energy. There may not necessarily be more storms. In fact, some of the evidence suggests there might be slightly fewer storms, but there will be more intense storms. And a study came out in the last month or so indicating that there is a documentable increase in the intensity of storms over the last several decades. But the key question that is harder to answer is what the impacts will be on New Jersey. On the one hand, warmer ocean waters might make it easier for hurricanes to survive as they move out of the tropics towards the mid-Atlantic. But changes in atmospheric circulation associated with climate change could also change the tracks of storms. And I would say right now, this is still a question that's the subject of active research, and the jury is still out on this one as well.
Thank you so much, Tony. That was a fantastic presentation, and you're very patient with all the questions, and we thank everybody for joining us today. I want to let you know that we will send a link out to today's recording once we have it posted, so you'll all get it. And we are sorry we couldn't get to all your questions, but your questions and your feedback have been really helpful to us, and they will help guide us as we develop materials and additional topics for this Climate Change Resource Center to address over the coming months and years, hopefully. We hope you'll join us for our next webinar. It'll be this Wednesday, June 3rd at noon, at which Professor Robert Kopp will speak on sea level rise in New Jersey. There's also, you can join us for any of the other Climate Academy webinars that you see on the website. And you're also welcome to join us for a two-part workshop on rebuilding New Jersey after COVID-19 that will be held on June 12th and June 17th. And that registration information is also on our website. So once again, thank you again, and taking the time to join us. This concludes today's webinar, and we hope everyone will be well. Thank you.